polyethylene. Polyethylene is a versatile and widely used thermoplastic essential in industries like packaging materials such as plastic bags and bottles, for construction, pipes and insulation. It plays a crucial role in various industries due to its versatility, durability and cost effectiveness. Polyethylene is used in various industries due to its excellent chemical resistance, lightweight nature and flexibility. Definition: bulk polymerization involves the monomer molecule and initiator and a chain transfer agent. The monomer is taken in the liquid state and the initiator is dissolved in the monomer. Height rate and degree of polymerization occur because of the high concentration of monomer. For polyethylene, this includes the direct polymerization of ethylene gas under high pressure or catalytic condition. The reaction is carried out in a closed system, allowing for better control of temperature and pressure, leading to higher polymer yields. Fundamental principle of bulk polymerization for polyethylene. Initiation: the polymerization begins with generation of free radicals react with ethylene monomer, which is heating the initiator to create radicals and using chemical compounds that decompose to form radicals upon reaction with the monomer. Second, propagation: the active site on the growing polymer chain react with additional ethylene monomer. It creates a longer polymer chain. This step continue rapidly as chain keeps reacting with more monomer. It may involve 1,000 monomer units being added to the growing chain, leading to the formation of high molecular weight polyethylene. Termination occurs when the active growing chain loses in reactivity. This can happen via combination. Two growing chains react to form a single polymer chain. This propagation, a growing chain transfer a hydrogen atom to another chain. This method can influence the final properties of the polymer, such as its molecular weight and distribution. Advantage and disadvantage of bulk polymerization for polyethylene. For advantages: first, high purity, no solvents are used, there is minimal contamination from impurities. This leads to cleaner final product. Second, cost effective. The absence of solvent simplifies the process, reducing equipment and processing costs. Second, the system is easier to manage, leading to cost-saving production. Control over properties by adjusting parameters such as temperature, pressure and the amount of initiator and properties of the resulting polyethylene. For disadvantages: heat management issue. The exothermic nature of polymerization reaction can generate significant heat. This can lead to localized overheating, uneven polymerization and even system failure. Second, viscosity challenges. As the polymer chains grow, the viscosity of the reaction mixture increases. This makes effective stirring and heat transfer challenging, leading to potential inconsistencies polymer. Last, limited molecular weight control. Variability in molecular weight can affect the mechanical properties of the final product, making it less predictable for certain applications. Lastly, example of products and application. First, high-density polyethylene is used for making pipes, containers, and industrial drums. Second, low-density polyethylene is used in plastic bag, film wrap, and flexible containers. Third, linear low-density polyethylene is commonly used in stretch films, plastic wraps, and food packaging.
So, let's start with the definition of solution polymerization. It involves dissolving the monomer in a suitable solvent along with a catalyst to initiate the polymerization process. The solvent plays multiple critical roles, such as a medium for the reaction, dissolving reactant and facilitating polymerization. The second one is it helps in heat regulation by dissipating the heat generated during the exothermic reaction. The third one is it provides control of properties, enabling better regulation of molecular weight and polymer branching. These factors make solution polymerization an efficient method for producing high-quality polyethylene. The next one is the key principle and condition. The first one is the process relies on catalysts such as xylenata to control molecular properties. The second one is hydrocarbon solvents like hexane or toluene ensure a homogeneous reaction environment. Precise temperature and pressure control is essential for polymerization efficiency. The last one is chain regulators such as hydrogen are introduced to control molecular weight and avoid excessive chain growth. As for the condition, monomer purity is crucial to avoid catalyst deactivation. The second one is an inert atmosphere like nitrogen is required to prevent contamination. The third one is effective heat management, ensure stability and prevents polymer degradation during the reaction. For the advantages of solution polymerization, the first one is the presence of a solvent makes heat removal easier, reducing the reaction instability. The second one is it produces polymer with low viscosities, making handling simpler. The last one is it specially suitable for producing high quality polyethylene with uniform properties. For the disadvantages, solvent recovery and recycling can significantly increase the production cost. The second one is residual solvent in the product may impact purity and safety, which is a critical concern in applications like food packaging and medical devices. For products and application, the first one is HDPE, which is valued for its strength and durability. It's used in packaging like milk jugs and detergent bottles. The second one is LLDPE, which is both flexible and tough. It's ideal for plastic bags, including grocery and trash bags. The last one is UHMWPE, which is extremely tough and wear resistant. It's used in medical implants such as artificial joints and prostheses. For emulsion polymerization, it is a process where monomer particles are emulsified in water using a surfactant to form micelles, which acts as a tiny reactors for polymerization. The process starts with emulsification, followed by initiation using free radical initiation, and concludes with polymerization of the monomer droplets. The key principles include the stabilization of the emulsion by surfactants, free radical initiation, and the use of water as the reaction medium. Emulsion polymerization offers significant advantages. It enables the production of high molecular weight polymer with low viscosity, facilitates heat dissipation during the reaction, and it is eco-friendly due to the use of water instead of organic solvents. However, it has its challenges such as requiring surfactants which may leave residues, complex post-polymerization purification, and the need for advanced technology to recover emulsion polymer in solid form. Water-based polymers are eco-friendly materials produced via emulsion polymerization with water as the medium. Examples include acrylic polymers for paints and sealants, polyvinyl acetate PVA in adhesive, and styrene butadiene rubber SBR for carpet backings. EVA is used in flexible packaging, while polyurethane dispersion and VAE copolymers are common in coatings. Natural rubber latex is widely used in gloves, balloons, and mattresses. These polymers are valued for their safety and sustainability. Thank you, that's all from me.
Suspension polymerization method in context of polyethylene production is involve forming monomer droplets in an aqueous medium, then suspending them through mechanical agitation. Then droplets act as tiny reactors where polymerization occurs. Then we move to fundamental aspect of suspension polymerization. We got 4 aspects, which is medium, stirrer, polymerization reaction, and initiator. Firstly is medium. The suspension polymerization process uses a liquid medium, usually water, to suspend the growing polymer particle. Secondly is stirrer. Stirrer is mechanical agitation. It's used to mix the monomer in the liquid phase. Strong stirring tends to produce smaller polymer particles, while milder stirring results in larger particles. Thirdly is polymerization reaction. Polymerization occurs when the initiator reacts with the monomer to form polymer chains. Lastly, we got initiator. An initiator or catalyst is a key component that triggers the polymerization reaction. It is responsible for generating free radicals or active species that start the polymerization of the monomer. The initiator is typically dissolved in the monomer phase and then distributed within the liquid medium. We got advantages and disadvantages of using suspension polymerization for PE, which is polyethylene. The advantages is excellent control over the size and morphology of the polymer particles, typically ranging from 50 to 500 micron in diameter. Secondly, we got capable of producing high molecular weight polyethylene, which is important for application requiring strength. Lastly, we got fine control over the polymer properties such as molecular weight distribution. Okay, we move to disadvantages of using suspension polymerization for PE, which is polyethylene. It is less versatile for certain
monomers that do not readily dissolve or disperse in the aqueous medium. Secondly, is more challenging to achieve very high molecular weight compared to other methods such as solution polymerization or gas phase polymerization. Lastly, is separation and washing of the polymer particles from the suspending medium can be labor intensive. Application of suspension polymerization for PE, which is polyethylene. We got 4 products and application itself. Firstly is high density polyethylene pipes. It is used for gas distribution pipes or drinking water supply pipes. Secondly is high density polyethylene household goods, such as trash bin or laundry basket. Thirdly, we got high density polyethylene films, such as grocery bags or stretch wrap films. Lastly, we got blow molded high density polyethylene bottles and containers, such as milk and juice bottle or shampoo bottles. Now I'm going to talk about gas phase polymerization. Gas phase polymerization method as it pertains to polyethylene production. The heterogeneous reaction between monomer gas and solid catalyst takes place in the fluidized bed reactor to produce the polymer product. Core principles and conditions involved in gas phase polymerization. The reactor is essentially an empty cylinder with an expansion zone at the top to reduce the gas velocity and help prevent any fine particles from flowing out of the reactor and into the recycle compressor, and a distributor plate at the bottom. Heterogeneous zygonata or metal-locking catalyst or pre-polymerized catalyst, particles are continually introduced into the reactor, ready to react with the fresh monomer being fed at the bottom of the bed. Active species diffuse through the particle, through the pores, and then into and through polymer covering the active sites. Continual accumulation of polymer causes the particles to grow from an original diameter, the order of 10 to 50 microns, to a diameter of several hundred microns when they are removed through a product discharge valve. From there, they go into a series of degassing tanks to separate the unreacted monomers. The gaseous recycle stream is compressed, cooled, and afterward mixed with fresh monomers, hydrogen, and eventually other compounds, then fed back into the reactor. Here's the typical reactor dimension and operating condition that can be found in the table 1. There's advantages and disadvantages of gas phase polymerization for polyethylene. The advantages is producing polyethylene with a narrow molecular weight distribution. Secondly, is more energy efficient and faster compared to other polymerization methods, such as suspension polymerization. It is leading to higher productivity. Lastly, is simpler and more cost-effective than slurry or bulk reactor. For disadvantages, is the polymer particles can sometimes agglomerate, leading to clogging or blockage of the reactor. Secondly, is particle size can be harder to control compared to other methods like suspension polymerization. Lastly, is control over polymer branching is more limited compared to other methods such as solution polymerization. Example of product and application of gas phase polymerization for polyethylene. First, we start with linear low density polyethylene films. The product is stretch film. It is used for wrapping and bundling product, providing protection during storage and transportation. Other than that, we got food packaging films. It is used for packaging fresh produced meat and other perishable goods. And we move to high density polyethylene bottles. The product is detergent bottle. It is strong, durable containers for household cleaning products. Other than that, we got shampoo and conditioner bottles. It is lightweight and impact-resistant packaging for personal care products. Lastly, we move to high density polyethylene pipes. Firstly, we got water supply pipes. It is for municipal water distribution system. Lastly, we got gas pipelines. It is for the transportation of natural gas or propane.
And now, I will explain one by one about polymerization method. And the first one is bulk polymerization. For bulk polymerization, the efficiency of the bulk polymerization is high efficiency and it's a minimal waste. For the cost is a moderate cost, and the polymer properties is high molecular weight and low density. For the scalability, it is moderate scalability. And the control over product is limited control over branching. For the second one, I will explain about solution polymerization. Solution polymerization, the efficiency is high efficiency and the moderate waste. The cost of the solution polymerization is high cost, and the polymer properties is higher molecular weight and high crystallinity. But for the scalability is high scalability. The control over product is good control over molecular weight and branching. Next, for the emulsion polymerization, the efficiency is high efficiency and the low waste. And for cost is a moderate cost, and the polymer properties is low molecular weight and low density. And for the scalability, same as solution polymerization, which is high scalability, and the control over product is moderate control over branching and molecular weight. Other than that, for suspension polymerization, the efficiency is very high efficiency and the minimal waste. The cost of suspension polymerization is moderate to low cost. The polymer properties is high density and high crystallinity. The scalability is very high scalability, and the control over product is excellent control over polymer properties. The last one is gas phase polymerization. The efficiency of gas phase polymerization is high efficiency and low waste. And then for the cost is moderate cost, and the polymer properties is high molecular weight and high density. For the scalability is high scalability, and the control over product is excellent control over molecular weight. In summary, for polyethylene production involve polymerization method, and each method has their own specific needs, advantage and disadvantage. Bulk polymerization is efficiency because it high purity and cost effective, but bulk polymerization have heat management issue. For the solution polymerization, it offers flexibility in controlling molecular weight. For emulsion polymerization, it provides high molecular weight polymer with low viscosity. And the next, for suspension polymerization, is advantageous for uniform particle size. Lastly, for gas phase polymerization is widely used for its cost effectiveness and scalability. Understanding the ability to process very high molecular weight of polymer to low viscosity polymer in itself also plays a major role in anticipating the needs and tailoring of polyethylene. As per industrial use, the most effective approach varies based on the properties and use, enabling progress in material science and increasing the usefulness of polyethylene. I think that's all from me. Thank you.